Today we have no camera because I just forgot it to take it with me, but I'm glad we have the cable at least. Okay, so what we're gonna be talking today is the two basically major things in anything in deep learning that you really need to understand very, very well, and which will have an influence on things like how you train your models, basically, because we're gonna train some models and they're gonna do something very interesting and important. So there are two basic pillars. One is coming from sort of like calculus, mathematics, and we're gonna use it heavily. And the second is like how to do these. So the first one is called gradient. Raise your hand if you haven't heard the word gradient before. So everybody knows what a gradient is. Awesome. And then how to compute it efficiently for very weird functions. That's the algorithm called backpropagation. Okay, so we're gonna touch this. If you heard this before, that's okay, so feel free to leave. Feel free to stick around and maybe just have a refresher on that, because it's like a really basic pillar of. If there is something you need to know in machine learning or in training deep neural networks, there is just a single algorithm. It's called backpropagation. There's like very few other algorithms actually. This one is very important. Okay, so this lecture we're gonna start some refresher on supervised machine learning. Although I remember some of you had machine learning before, which is great. Then when you go into some little bit of mathematics, of derivatives, I don't know, I mean, raise your hand if you love mathematics. Okay, good. And the rest is like, I don't know, it's complicated. Okay, so partial derivatives and gradient will be one part of that, and then the algorithm of backpropagation. This is the motivation. I mean, motivating this lecture means we have to have some basic building blocks. Like without understanding this, the rest will make less sense. I mean, it's okay, you can work with stuff. You can work with, you can build a company and get rich, without understanding these nitty-gritty details. That's okay. I'm looking at you because that's what you're doing. But this is a master course. I mean, master, bachelor. So I mean, this is university, so we should understand this. So let's start with some notation first, because we're gonna be using some heavily, well, not heavily, but we're gonna be using some symbols and math stuff here. So just to understand that we're on the same page. So we're going to be working with vectors, and in linear algebra, if you remember, or in physics, or in mathematics basically, vectors are usually written as columns, right? These are column vectors. So you multiply matrix by a vector. Can you do this? Yes, matrix by vector to get another vector. So these are column, and usually we're going to use like boldface and lowercase. And what we're gonna do is actually we treat them as row vectors. So basically on a line is where we just transpose it. So this vector is sort of a row vector, which is also a matrix with one row and three columns, right? So nothing should be surprising so far. It makes sense? Good, but there's a trick. So sometimes many times we're just gonna say, okay, one-dimensional array, which is just a bunch of numbers. It's a list of numbers like this: 1, 2, 4, 6. It's a bunch of numbers, and we're gonna treat this as a vector. So we're not gonna be pedantic about like being column vectors. So just bear in mind, like we'll be mostly using vectors as a row vector. So this will be one assumption which is kind of different from the pure mathematical notion of vectors, where you always have to write like X transpose to make it a row vector and stuff like that. Okay, so usually this will be like a bunch of numbers, because it's very convenient to work with a bunch of numbers in computer science. You just put them in an array or whatever. Okay, cool. So first things, and then obviously we have matrices. So we're going to be using capital letters and bold for matrices. And here this is a matrix of dimension 2 times 3. So 2 rows, 3 columns, and we're indexing from 1. I mean, sometimes we can be indexing from 0 to n minus 1, sometimes from 1 to n, depending on the context. So be aware of that. Like there's no unified terminology which everybody's using. It's like everybody's using which basically fits the purpose. So, and then we have scalars, which are just simply real numbers, a, b, and c. Nothing should be surprising. This is just setting up the stage. So then we also have obviously we have some ambiguity in the notation. So a dot can mean multiple things, and it depends on the context. So we can multiply two numbers. Yeah, makes sense. We can use it as a dot product, which basically takes two vectors and is multiplying each element from one vector, excuse me, with the element of another vector at the same position and summing them up. So it's a dot product. Everybody knows dot product? Okay, excellent. And then, of course, we might be multiplying matrices, matrix, multiplication. And then for, again, using this sort of dot thing, where we usually don't actually write it. We just write YZ or XY, XW. Which, if you, so everybody can multiply matrices here. If you cannot multiply matrices, use your free time to really recall how to multiply matrices, because this is going to be like, the only crucial thing here is like, oh, can you multiply vector by matrix, matrix by matrix, and stuff like that. You don't need much more from linear algebra for deep learning, but you have to know like how to multiply matrices and what the dimensions mean and things like that. We'll come to that again in a couple of details, but just for you as a warning, you have to be really familiar with that stuff. Okay, any questions so far? Anything surprising here? Great. So some basics of machine learning, because supervised machine learning, what does it mean? Why we call it supervised, and why does it matter? Because in supervised we are given some data. So we have some supervised learning problem, and usually the data or data set is a bunch of pairs of input-output. This is very simple. So we call them labeled examples or annotated examples. And here, each input, basically, we take them as input-output. So the input is some d-dimensional vector, usually of real numbers, of some precision in computers. So we're usually using double representation, like 64 bits or 32 bits, 16 bits, depending on the context and how big your GPU is and stuff like that. But this is like a bunch of numbers. And we call them, in standard machine learning, we call them features or attributes or statistics. Is there anybody from statistics? Covariates? Some people are calling them covariates in the statistics, I guess. In machine learning terminology, these are features. Okay, so this is what's, how we describe the input. We can talk about examples later. And this output thing, or we call it label, yn, is something which is associated with the input vector. Okay, so a simple example of input-output, not from language, but from, let's say, picture recognition, could be that these features are, it's a list of pixels, and each of them has some value. If you take like grayscale picture, so it has values from usually like 0 to 255, and you can take a picture which is a square, but you can just basically take all these features and all the rows in the picture or the pixels and just concatenate after each other, have a basically long vector of pixels. And this could be your input. And the output could be, if you have a simple binary task, could be, oh, is there a cat or not? Like a cat recognizer would take, all these pixels, these are pixels, turn them into just a single vector by just, going through rows, and the label would be in 0 or 1 typically, and saying like 0, oh, there's no cat in this picture, and 1, there's a cat in this picture. Any questions?
Yes, I didn't exactly understand what is the label actually. Is it the value that the X will take, or?
This is the value. This is how we are labeling. This is some information we want to predict. So this is, if we are interested to say, oh, this picture is a cat, yes or no, this is how we encode it here. And in the picture, obviously, we want the machine to understand the picture, so to say. So the machine should be able to, just by looking at this picture, whatever looking means, to say, oh, there's a cat or there's no cat.
So the picture is X.
Say again? The picture is X. Yes, exactly. So this is X. This is the picture. We turn it into this vector, because it's a vector. So this is X, and this is Y. The Y is the label. Any other questions? Okay, great. So this is the basic setup. It can be more complicated, but this is the binary setup. We have the other example from last lecture, the sentiment classification of on IMDb, like the movie review, positive or negative. So here the y would be positive or negative, or positive yes or no. And the question is how to turn text into features. We'll come to that, yes.
So can we represent that as a function, like if of x is like y?
Yes. Exactly. So what are you doing here? Simply because we turn our problem into vector in, number out, or numbers in, numbers out. You know, in mathematics, numbers in, numbers out means there's a function which is doing this for us. Like, there's a function, and we can see our machine learning or AI is basically it's a function. It takes the input vector and producing some outputs. Typically, it could be one single value, or it could be also vector. We'll come to that. So here we call it a predictor or a model. It's a function, and you know, if we have just a single output like a binary, then this would be a real number. So this is just a single number. We might be actually interested in, for example, in multi-class classification where we have different classes. For example, we want to classify a document into sports, politics, or business. So we have 3 classes. So we're going to model this as a vector of real numbers of the size of the number of classes. So what we're going to do is to take some input and to predict is here 1, 2, 3. So there will be some numbers which will correspond to something here. So what do you think could be interesting here to predict? So if we want to predict, so this is the document. We don't know what is in there, like how to represent it, but we're outputting 3 numbers corresponding to 0, 1, and 2, sport, politics, and business. So what do you think could be these values here? What could be interesting for us to predict? The probability of what? Exactly. So this is going to be a probability of the corresponding class. Okay, so these will be 3 probabilities. Anything else we should impose on that? So probability could be between 0 and 1. Do we want anything else maybe? I mean, it could be probabilities, that's great, but maybe even more restrictions, yes?
They should probably all sum up to 1.
Oh, they should. Okay, they should sum up to 1. This is interesting. You know why?
Yeah, typically use a softmax for that, and that means we have an actual probability space over the outputs.
Okay, good. I mean, if, depending what's first, chicken and egg, but you can use softmax and things like that, we'll come to that. But basically, it will give you a very nice probability distribution. And probability distributions, if there's like categorical things, they have to sum up to 1. Like you have different events in the probability, and the total probability is 1 by definition of probability theory. So this is nice. I mean, actually, it doesn't have to be like that, because if you want, yes. It doesn't have to be like that. It doesn't have to sum up to 1 if you're just interested in like the biggest value here. But it's kind of nice because it has like some probability properties. You can say, oh, with this probability, I'm predicting sport. Yes?
What is if we classify, for example, a news article
Mhm.
and we fit perfectly 2 categories in it?
So, okay, what you're asking is like, what if we have, what if the label, well, let me come here. So let me finish this, because this is exactly what we said. Like, we're predicting some numbers and they sum up to 1. Okay, because it makes sense. And you're asking like, what if the label is actually both sport and politics? Is it your question?
Yeah.
Okay, we call this multi-label, multi-class. I mean, we have multiple classes, but we have multiple labels. So we need to predict something different. We need to predict basically all those categories should be 1 and all the other remaining should be 0. This is how you can label this. And so multi-label is much more trickier for many reasons, because you need to learn like multiple things at a time. The evaluation also is a little bit trickier, because you cannot use just accuracy or F1 score, because you have to take into account like, what if you predict more, what's the overlap? So you're using something like Hamming distance and things like that. And you can turn multi-label into single label, where you train different models or predict them independently. We're not gonna touch multi-label that much, because this is not really like I mean, it exists, it's a problem. Sometimes the only solution is multi-label classification. Most of the time, we're gonna be dealing with like single class classification only. Okay? Yes?
What we have like an input and content like for example it's about IE and it's not able here like sport or politics or business. What would be
Okay, so you're saying like, what if our document is not in one of these categories? Yeah, then you choose a wrong model of the world. I mean, you're deciding like, okay, how many classes do I have in my data set? And if you have something which doesn't fit in your data set or in your label inventory, so to say, then either you change, you have to change your labeling scheme and your classes and extend, I don't know, whatever could be there, another topic, celebrities, and add it to your data set, or just maybe this document is an outlier and you can somehow ignore the fact it's a different category and don't classify it at all. It's up to you. You have to design. This is everything up to you to decide. How many classes, what's your problem, and things like that. Okay? Any questions? No. Okay, so let's move on. So now what do we have? Okay, we have the data. We have the function. And the question is like, what is this? Okay, so the core question is like, what is this function actually? Like, how this function actually works? How do you take a bunch of numbers and turn it into another bunch of numbers? What function is it? Like, is it y equals x squared? Yeah, not really. I mean, it's a function, but it doesn't solve the problem because actually first it doesn't make sense for vectors. I mean, it does, but I mean, it's more complicated. So the question is like, what is this function? And basically the whole deep learning stuff is about like, oh, how can we model this function and how can we design this function? So this function is some function, we don't know which function, but it has some parameters. So f of x, and there is something called, how do you call this symbol?
Theta?
Theta, exactly, theta. In LaTeX with backslash, so theta. And this is something like you can decide what could be a theta. Okay, so give me an example, something. So we have a polynomial of degree 5. What could be the parameters of that? You know what? Everybody knows what a polynomial of degree 5 is? Like ax0 plus, ax plus bx squared plus, plus c and so on, and there is one value plus z. So what are the parameters? These things, yeah, coefficients in polynomials. So for example, these are coefficients, and these could be parameters. And for each polynomial, we can tune them differently, and we get a different polynomial. Okay, so this is one example. I mean, but as I said, like our functions are not usually polynomials. There will be something much more complex because can you use a polynomial to turn a text into politics? And so most likely not. It will be much more complicated. Okay, but these are the parameters which you want to learn, and we need to find such a set of parameters, theta, which gives us something that perform well on some unseen data. So we want to find something which, yes?
Would theta then be something we call model weights in other?
It could be, exactly, we can call this weights also in deep learning. In general, it's our parameters. Weights are called in deep learning, and these will be basically some matrices maybe or some other things, yes. Good, and we want to find such those that they perform well on unseen data. And the question is like, okay, so now we have the data which we are given, so we have pairs of input-output. We might have some part of that which is test data, so we just split the data into train and test. This is what we discussed last time already, so never test on your training data, test on something unseen, but train on your training data. So we're gonna be training our function, so to say, or finding the parameters on the training data to find the best performing ones here. And then we'll test it on the test data. So this is basically the part of training or parameter estimation. So we need to find such parameters that we perform well. How do you know you perform well? How can you measure you're performing well? So this example with the cats. So you are given a bunch of pictures and you are giving a bunch of corresponding labels. How do you know you're performing well if you have a function? Can you measure like I'm performing well?
In the binary case, you just count how many you get right or wrong.
So you're saying, okay, yeah, what you're saying is like if your function of some input gives you something which is correct, you say +1, and if it's not correct, you get like 0, something like that?
No, the other way around, typically. I think.
Oh yeah, the error. So you're measuring error.
Yeah.
Okay, so you would say if it's an error, you would give you would get like error plus, and here nothing.
Yeah.
Yeah, the other way around. Okay. Okay, that's okay. You can use that, but it's a very strong signal. Like it's not giving you like how wrong you are. It's telling you like, oh, you're wrong, or you're not wrong, which is sort of like a discrete. And we might do something much more fine-grained.
Maybe we had different probabilities for the different classes, and maybe something that's weighted.
Oh, okay. So you're saying we have different probabilities for different classes. So we might have these probabilities, and then the true label would be different probabilities, and we might somehow compare these.
Yeah, and we don't get -1 or +1, but based on the difference to the correct answer.
So exactly, you're up to something. You're looking into the difference between the truth and the prediction, but in contrast to your case, where you just say like 1 or 0, you're saying, oh, what is the difference of the values? So you're looking much more fine-grained. So if your classifier is very wrong, then you penalize it more. And if it's almost correct, you penalize it less. Does it make sense? Like this intuition, you're penalizing your classifier for something, and you're penalizing the worse the prediction is. And how we're gonna call this is called the loss function. So how much we're losing actually on each prediction. So we have here the true label. So this is an example for just a single number prediction, like a real value. So we have something which is the true label, so real number, and we have the predictor's output, and we're gonna get some positive real number, which is loss, and it's similar to your error. Like the bigger the loss, the worse I'm performing, and the smaller the loss, the better I'm performing. Does it make sense intuitively? Okay, and it's actually measuring how big an error was made. So now, if you know already, like we're measuring loss, do you have any idea like what a loss function, like an example of a loss function for two numbers could be?
Like the difference between the two values.
Yeah, so you're saying like simple one would be the difference between two values. Okay, y hat. This is by the way called hat. So y hat is the prediction typically. So you're saying the difference. Yeah, what if this were 0 and this were 1? How can you fix that? Because now it's not positive anymore.
We could, I don't know the word actually, between two brackets, like, I don't know.
Like that, absolute value?
Absolute.
Okay, that could work. Anything even much easier? Wow, now you're getting fancy. Mean square error. So what does it mean? Like how can you fix this?
So just the L squared instead of the absolute value.
Yeah, that will work. Okay, that's called mean square error, exactly. And this is it. This is a mean square error. This is one example of how to make a difference between two numbers positive, and the bigger the difference, the bigger the error. And it's actually growing quadratically. Quadratically, yes, quadratically. So the bigger the error, the bigger the loss. Okay, does it make sense now? Like we're measuring the difference between those two for those who haven't had machine learning before? Okay. And of course, this is just for one single example, and we want to have it for all the examples in our training data set. So we have n points in our training data. So what we're going to do is we need to minimize it for each of those, and we just take the average. So the average loss, basically. So this is for each example is the function which is predicting the y hat. This is the true label. We're taking the mean square error, and we're just summing them up and making an average. And this fancy thing, minimizing theta, means like, oh, we wanna minimize this thing with respect to theta. So we wanna find such theta that this thing, this empirical risk or average mean square error, is as small as possible. Because it means then we could find a function which kind of almost fits the training data. That's what we wanna do. We wanna learn a function which kind of mimics what we are given in training data. So for all the cat pictures, it would give you 1, and all the not cat pictures will give you 0 or close to that. And this is how we are actually modeling it, the training process. Okay, so this is, yes, you have a question.
Is there a reason why we square instead of just doing the absolute value?
There is the reason why we square instead of just absolute value, and the reason is mathematical convenience.
The absolute value function isn't continuous at the point 0, so there's computational problems with that.
Yeah, that's not a computational problem. I mean, but you're up to something. Like continuity will make sense later, and you will understand why square is actually kind of convenient. But we could go with absolute value. I can guarantee this would work. This won't break. Maybe it won't be that convenient to do some operations later on. So the key approach to supervised learning is we need to find a good parameter vector. Well, we call it theta star, whatever. So something like the true theta or theta star, some good parameters by minimizing. Oh, we need to minimize the average loss. Okay, so now, we turned our very big problem of, you are given a picture and a label. Okay, we represent it as vectors. Then we say, we can model as a function, and the function has some parameters, and we want to make this function or the parameters small. We want to minimize a function. We turn a big problem into a problem of minimizing a function. It's pretty convenient, right? I mean, what we just need to solve for training is like how to minimize a function. Make sense? Minimizing a function. Okay. Yeah. Can you minimize if you're given a function, can you find a minimum of a function? If I give you a function, so for example this. I give you this function. I mean, okay, so now pretend you don't see actually, the left part, you don't see it, but you're given something like 3 minus sinus 2x over x. Can you find a minimum of this function? Yeah?
You take the derivative and then
Ooh.
solve it for 0.
You take the derivative and solve it for 0 to get what?
The slope, it's like the ascent, and the...
But if you solve it for 0, you get something else, yes?
We get all the means and all the marks.
You get yes, exactly. If you solve, so this is like the high school mathematics is, I guess, I hope you had it in high school. So you take a function, you take its derivative, so that's why you all learn all these derivatives, and then if you take the derivative and put it to equal to 0, solve it for 0, you get all these minima and maxima. Is it flexion point or something like that? I don't know. I forgot its name. So local minima and maxima. This is what some of you or most of you should have learned in high school or in Calculus 1 in here, at the university. So, okay. For complicated functions, this will be not trivial and this will be like pretty nasty to do. But we'll start with something like the derivative. So this is a good point. For minimizing functions, you need derivatives, and there's a reason why so. So let's dive deeper, okay? So is there anybody who hates mathematics? Don't be shy, it's okay. You can leave now, that's okay. I mean, no, we're gonna do deep dive, but not much. I mean, I'm pretty sure you know everything already. This is like, this is not rocket science, if you think about it. Okay, so we have a function of a single variable. Yeah, everybody knows that. So we're using this Euler's notation, and the naming of this function is like very arbitrary. So we're using f for the function, x for the input, and y for the output. Could be anything, but usually we're using these 3 letters, okay? And the function is from some domain to some codomain. Real numbers to real numbers. So let's stick to these real numbers to real numbers function, okay? Something like x squared. It's a beautiful function from x to y. And we might do function composition, which basically means you have one function first, and then this is encapsulated in other function. So usually you would write this, but some people are using this very awful notation because you don't know what's first, if g or f. But this is kind of clear, right? I mean, for example, x squared, this is a nested function. You start with a squared, and then you put it into the exp. No surprises here, I guess, okay? Cool. Good, and you said like you take okay, we need to talk about lines. What are the lines in Cartesian dimensions? So usually line is some sort of set of points, because in mathematics everything is a set. But it's basically tuples of x and y, and they have some, excuse me, they can be expressed by a linear function, But what we are usually know as a line, what we usually use as a line is this slope-intercept form. So y equals ax plus b, right? I mean, there's a line coming from infinity to this, and the a is telling like how big the slope is, how much is the growth if you grow x, how much the y grows, so linear, and the b is just intercept, like how much you move it up or down. Make sense? Good. So now we're talking about a slope, and actually, if I think about slopes, like I'm thinking, okay, so the line goes dead or dead. I mean, slope to me is something like the angle. Like if you have a slope on the I don't know, in the mountains, like skiing, I mean, there's like 12-degree slope or something like that. But there's so we usually use, oh, by the way, this theta is very much different theta from the parameters of the function. This is just the angle. So be aware of this ambiguous notation. So we have this angle here, and if you do some basic trigonometry, you can find that basically the alpha is the tangents of this theta. So if this like 90-degree slope, the slope is infinity. It makes no sense. Then think about it. And then if the angle goes to 0, then the a is becoming 0. Okay. So this is the connection between sort of like a number between, could be anything, and the actual angle if you're thinking in degrees of slope. Does it make sense? Cool. Any questions? Good. So we have lines. And now let's coming back to our example. We can approximate function by a line at any point. So, for example, if we are, I don't know, let's give me some like this point, we can approximate it by a line. So this is going to be some line, so quick question. This is a line. So what will be its slope? Will it be positive or negative? It's going to be negative slope. So it's going to be y equals minus something times x plus some coefficient. Why? Because it's going down. You have, if you go to the right, the y is not growing, but it's decreasing. Okay. So that's a negative slope, some negative number, and some other coefficients. Okay. And then now we're coming to the derivative. So, derivative is interesting. So the derivative is telling us basically the steepness at any point c. So if we are at this point c, the derivative, it's telling us exactly the slope of this function. So what you're doing is how can you find a slope of a function? I mean, what does it mean? So if you have this function like that and 2 points, you start at this point, and so this is x. Oh, sorry. This point and this point. So somehow you're trying to approximate this line. And what you're doing is, this is c and this is x. What you're trying to do is to make this smaller. So x is going very close to the c. So you're moving here very close to the other, which gives you much more better estimates of the slope actually. So, and this is what we are called the derivative at c. So this is the limit. So you're taking this closer to here, and basically the slope is the rise over run trigonometry. The angle, like if you have a triangle, if you're gonna get the slope, it's this rise over run. Do you know this from trigonometry? So sinus is the rise over, what is this? I forgot this name. Say again? Hypotenuse, yeah. And cosinus is run over hypotenuse, and tangents is rise over run, and you get the angle. So this is basically what derivative is doing. It's telling you like what's the slope, and it's taking the limit because you want to be as precise as possible. Coming closer to 1 point. So, but this is a refresher. So if you need to refresh this, I have some references later on which you can just look up to understand more of derivatives if you really need to. So now we know how to compute the steepness. It's the derivative of the function. And this is great. So we can use this definition to compute any derivative for any point for this function. Okay, can you compute a derivative of this function using the definition? You could, but it's going to take a while because you need to avoid all these nested limits and blah, blah, blah. So maybe what you need to do is to have a function which is a derivative computing function, which takes a differentiable function f as an input and produces another function g that, for any c we're given, it gives you the derivative of the original function. What does it mean is that you know it already. So I'm going to tell you, this is what you know as a derivative, basically. What is the derivative of x squared? 2x. Yeah. What we just did is we computed through the derivative computing function, and we changed variables because we could be like 2c to match this terminology, but we're just, not paying attention, and we're just, it's going to be 2x. So this is the derivatives everybody is being, calculating over and over in your math classes, the derivative computing function. And how can we call this function? Well, sometimes it's called like these f prime, like in physics. We call it sometimes d with respect to dx, or sometimes you call it d dx of f. Sometimes you call it df with respect to dx. Sometimes you call it dy with respect to dx, and all these nested things. So the notation is really messy because it's 300 years old. So everybody has been using a different notation. So what we'll be using is one of those usually, and maybe like this prime, like this physics derivative function. Okay. So any questions? Are you scared anymore of mathematics? Same. Okay. So it's not getting worse at least. Okay, that's good. That's good. Okay, so now we have these derivatives. And the question is, okay, so you know how to do the derivative of, let's say, x squared. How do you do derivative of something nested?
Use the chain rule.
Oh, the chain rule. Okay, everybody heard of the chain rule? That's great, because the chain rule is all you need, basically, for doing anything in deep learning. It's a chain rule. So the chain rule is the hammer, and you find many nails. So, and the chain rule is telling you, so the prime, the derivatives with the tick, with the prime, is called the Lagrange notation. So it's telling you that if two functions which have derivatives, so of the nested function g of f of x is the derivative of the outer function evaluated at fx times the derivative of the inner function evaluated at x. Okay, so what does it mean? X squared means you start with derivative of exponent function, which is itself, yeah. Derivative of exponent, so it's going to be exp evaluated at the input, which is x squared, times derivative of the inner, which is, we had it already, 2x. Oh, excellent. Chain rule. Can it be more complicated? Yes, I mean, the function could be like very nested and things like that. But there's an example in the appendix of this lecture where you can just really dig deeper into this chain rule of 4 functions and how actually does it, just go through and get familiar with that. So this is the Lagrange notation, and of course we have this very nested composing operator which says, okay, if you're using this for nested functions, we're gonna get the same, but just how we write it is very different. And as I said, like, I don't like this symbol because you don't know what to start with. So this is much more convenient to work with. Or the Leibniz notation, which is this very fancy, it looks like a fraction, but it's not a fraction. It's just a derivative of a function with respect to some variable. Which means then we're going to do the same thing, but the notation looks differently. So it's the derivative of the outer function evaluated at f times the derivative of the inner function. So you just see the messiness of the notation, but it shouldn't scare you. But pick one, get familiar with that, and then you will understand the others. That's how I did it. Like, I do understand this because this makes sense, like from a computer science perspective. Oh yeah, I mean, this is the output of the function. I put it through this and multiply with the other. Okay, I can do this. I can even program this. This looks very nested, like fractions. Because, I mean, it's telling me, oh, wait. These are fractions. I can, you know what? I'm multiplying 2 fractions and I'm going to do like, this, and I'll get this out. And wow, and it works. Like, it gives me this results, But for the wrong reason. These are not fractions and you cannot do this. But it looks like it's so convenient to do this, then you can understand, yeah, of course. Yeah, this is how it works. No. It's this is the true reason, like, behind the chain rule, not like multiplying 2 fractions which are not even fractions, okay? So notations kind of can be misleading. Any questions? Yes.
I just wanted to comment about the third one, but it can be helpful to like make sure you have all the ones, right? Like when you're doing the chain rule.
It might be helpful to do so, obviously, sure. It might be helpful to use this, and we'll be using this later on as well. But I'm just saying these are not fractions. That's a point. Okay, so now we have the slope. Well, what are we gonna do with that? I mean, you said like you equal it to 0 and solve it, and yeah, but that's kind of nested. So there could be better ways. So what happens if you have let's say, what happens if you know the slope somewhere? Oops. If you know the slope of a function and we are somewhere, not in this place, but let's say, so here we know the slope, and the slope is going to be positive. So it's going to be positive slope derivative. What can we use it for?
You know the directions of increasing and decreasing.
So if you're here, you know where the function is increasing here. So which also means like it's not decreasing. So it's increasing on the right. Like if you go here, it increases, and if you go here, it decreases. So that's what you know. Okay, this is an interesting information. So can you do something with that?
You can go into the direction of descent.
You can go into the direction where it's decreasing. Why? Because you want to minimize this function. So you want to find a minimum, and the minimum won't be like on the hills. It will be in the valley. So you need to go somewhere where the function will be smaller, which is going to be here. And the derivative is telling you, if you take a step here, so to say, in the opposite of the derivative of the slope, you will get somewhere where the function will be smaller. Does it make sense? Good. So what you gonna do next? So you say like, okay, I mean some number, I'm changing the x and I'm here. What you gonna do next?
I look at my new slope.
You look at your new slope, and then
You take a step again.
you take a step again. So it's gonna be here again. Okay, you take a step again. And then what?
Repeat until the slope is 0.
You repeat until you reach the minimum. That would be excellent. Or you repeat until you get out of your hardware or whatever. You repeat whatever, you're repeating over and over until some criteria. You have a question?
No, I mean, I know the answer, but I don't understand how it works.
You don't understand how it works yet.
I have an answer to that, how we get to know if we get a minimum or a maximum.
Yes.
But I don't understand why it works like that. But
You don't understand why it works. Okay, so does the gradient, the slope, I mean, does this derivative make sense to you now?
I know the answer, how we get minimum or maximum, we get the second derivative of that.
No, we don't have any second derivatives. We just have first derivative. It's telling you like it's rising or going down and how fast. So what is missing there? I'm just curious, like what is missing? So, I mean, let's get to the algorithm, and then maybe you can tell me like, if it's any clearer. So, again, what we want is for some x, we want to find such a value of x that the function is minimum. So we call it argmin. So minimizing with respect to x. So what we need to have is like we can get a value of f for any x, or actually we can evaluate its derivative for any point anywhere. So for any point, we can get the derivative of this function. So can we get a derivative of this function at any point? Yes, it's gonna be, so we need to compute that, the derivative of this function would be something like, I don't want to do this. Cosinus, I mean, some fractions, cosinus, something very nasty. I mean, do it at home if you want. You get the derivative computing function. So for each point, you can compute the f with respect to dx. You can do that. And then, we can start at any random value somewhere. I don't know, pick one, like this one. We start here. This is maybe a bad choice. So let's start somewhere else. Let's start here. This is going to be very easy, maybe. Okay, now, so this will be the direction and strength of change at x. So we have the derivative here of this. So Imagine there's a line, but we don't see this line. Imagine there's a line and it has a slope. This is going to be the slope. The higher the slope, the more it's rising here. So it gives you some strength of change at this point. So it means it's positive here. So the derivative f point x1 is positive, and it has some value. So it's some, I don't know, like let's say 3. Okay, and then what we're gonna do is to take this value, subtract this derivative, the value of this derivative, and multiply by something which is very fancy, Greek name eta, Greek letter eta, and we call it the learning rate. It's called the learning rate. And move the x somewhere. Okay, so let's say eta is 1. Why not? Let's take it 1 for granted. So what you're gonna do exactly is to take the value of the derivative at this point, which is positive, it's 3. So you're gonna move your x1 to x2 by 3 points. And you're here. You follow. Okay, good. Okay, now we're here, and we repeat. So we get the derivative at this point, which is going to be a line. So we're going to get something like, the derivative will be at x2 is going to be 0.001. So it's still positive. We're not in the minimum, but what we're going to do, okay, so we need to take a step again in the left direction because it's positive derivative, so we get this minus here. So we go left, but by very tiny little because we already have the very small derivative. Okay, and we can repeat this over and over, and what you see, we got stuck in this local minima. We found a minimum, but it's not a global one. Now, now does it make sense for you as well now? You don't know why. You don't know why? Still, this is the why question. No, sorry, okay, think about it, we can talk about this later at the exercise. Okay, cool, good. So how can we fix that? I mean, the algorithms kind of make sense, but can we fix it to kind of really find this part here?
You can take like smaller eta, like learning rate.
Oh, we're gonna take a smaller learning rate. Okay, so it's gonna be smaller, let's take it 0.01 maybe. That's a good idea. So again, we're here, first step, and the derivative is 3, which means we're just not moving by 3, but by 0.003, which gets us here. Ah, okay. Then the next step, again, and again, so the learning rate is telling us, the derivative is telling us like something about the function, but the learning rate is telling, we designed the learning rate to say like, okay, how much actually do I care, how much risk I'm taking in a way, far away, to go far away or to stick somewhere. And if you have very small learning rate, and you can change the learning rate over time, you will end up in some minimum. And it can be a local minimum depending on where you started. Because if you start here and have a small learning rate, you most likely end up in this minimum. So that's a tricky part. Like the initial conditions where you start and the learning rate influence if you find the minimum of a function. Okay. Any questions? So can you now build this? Could you actually program a thing that minimizes a function? Yes.
We have like a range for the learning rate, like between 1 and 0. Or
Okay, so what could be the derivative? What could be the derivative sort of range? What could be if we have y equals ax plus b? What is this? What could it be?
number.
Yes, and do we have some limits on the number? So the derivative could be anything between minus infinity plus infinity. This is basically, this is the real number. If it's 0, then your line is basically horizontal. If it's, you don't have infinity. Infinity doesn't exist, but it will be like super arbitrarily large, which means it will be almost like vertical line.
That's for the derivative. Like I did actually like for the learning rate. Does it like have to be between 0 and 1?
No, your learning rate should be somehow positive because if it's negative, you go the wrong direction. So it has to be positive, and it could be as big as you want. It really can be as big as you want.
But I think in this case case we could like get stuck between getting too far.
Exactly, yes. If it's too big, you're just jumping, over your function, and you never converge to something meaningful.
So the like a matter of process.
It's a matter of experimenting and kind of like you try and it doesn't work, so you change it and it works better. This is the only magic, in this algorithm. It's like, oh yeah, how do I set up the learning rate to make sense? Yes. Okay, good. Any other questions? Great. So we can minimize a function. We can now really minimize a function, like single value function, because the only thing you need is how to compute a derivative at any point, and then you just take a step and repeat. This is iterative algorithm. It's very easy, in a way, as long as you can compute a derivative. That's the point. Yes.
Two questions.
Yes.
One, how long do we search, and when do we swap directions?
So how long do we search? So the second question first. When do we swap directions? I mean, the direction is based on the value of the derivative. If your derivative is positive, so which means you always go in the direction opposing to the sign of the derivative, because it goes down. Because if you go in the direction of derivative, you go up, and then the derivative dictates you what the slope is. It could be a decreasing function or increasing function. And if you always take the opposite, you will always go down.
Yeah, okay, then we will get stuck and only find one minimum, right?
Yes, you can only find one minimum, exactly. This will find you just one minimum. So your algorithm will find you a minimum. Most likely it won't be global, it could be local. If your function is not convex, which means convex function has just one global minimum, but mostly the functions are not convex. And for how long you run this? That's a good question. You have to decide. Maybe number of steps, like 100,000 steps, or unless if there's two iterations of the algorithm and the minimum doesn't change, maybe I just stop here. So it's up to you to decide. There's some stopping criterion to be decided, or forever. You have a question?
Say we have optimized the loss function. Does it mean that we have a good model then?
Yeah, that's a good question. So by optimizing this loss function, you're fitting your training data basically by optimizing this loss function, because the loss function is getting smaller and smaller, which means you are modeling your training the data better and better. And if your loss function is 0, what could that mean?
Well, we have to find the optimum.
You find the absolute optimum. Like you learn all the training data, because you will have no misclassification or nothing. I mean, if your loss is 0, and your for example, square loss, if your square loss is 0, which means for all your gold labels, you are able to predict the true value. So there is a 0 loss. So you learn your training data perfectly.
But does it mean that the model is useful then?
Does it mean the model is useful then? That's a good question. So you have to test on your test data. Because sometimes what you can do, you can learn your training data perfectly, but it just means the model just remembered all the training data. And if you show it new data, it will just be completely random or useless. So the trick is how to build such a model build such a model by minimizing the loss function that actually will be helpful for something you've never seen in the training. That's the hard part, like how to design such a function which can generalize well. So generalization is the key thing. Okay.
Is there a trick that allow us to know if we are having a local minimum or?
Okay, so mathematical trick if there's a local or global minimum. I guess somebody mentioned here the second derivative, which will tell you exactly that. I think if you avoid the second derivative at 0, so I'm sorry, I'm pulling this out of my head. I don't remember exactly, but I guess the second derivative method will tell you something about the minimum. Yes, you know.
That's actually what I wanted to say. It's like we had a problem to analyze if we have maximum and minimum, and my solution was to get a second derivative, but second derivative doesn't always work. Can you say that it is maximum or minimum, or it has a case where it doesn't say if we get a minimum or maximum? So it's a nice solution, but it's not used in machine learning because machine learning has typical functions, and second derivative won't always tell you the right answer.
Okay, so look here. There's an answer. It's a free book, Jeremy Kuhn, very cool book online. You can buy it for whatever you want, $1, and it's yours. and there's a theory behind it. And as you're saying, like the second derivatives are actually, I mean, we can use them, but they are not used in machine learning for a reason, because they are super, they're expensive to compute. As we see later, we have functions which are actually very complicated, and even computing the first derivative is already like a lot of work. And then you have to take a second derivative, which is again like a lot of work, and it doesn't give you that. I mean, empirically, that just the first order minimization is good enough.
Even for computers, like.
Yeah, it's good enough. I mean, this is how neural networks are. This is how ChatGPT is trained. It works. Yes. Yeah, so you're asking, we're training a model and we're looking at the loss, and the loss is going down, but it's not going down anymore. And then you're saying, okay, so maybe we should start again the training with some other initial parameters to see if we go some better performance, let's say. This is what you're asking. Okay, and the answer is yes. If you have resources to do so, you can try different random initializations of your problem, and maybe you get some better results. The only thing that actually matters is, do you have enough compute time? Do you have enough GPUs or whatever you need to compute on? Do you have enough? And yeah, that's it. That's basically it. Like, it's if you have like thousands, if you can start a problem 1,000 times, then one of those will be better because of the randomness in the initialization. There's some randomness, and sometimes it's really unpredictable. Actually, the idea is that the algorithms should be somehow robust to the initialization. So some initialization of something are better than others, which is like a black art. So for some weights and stuff like that, you have some best practices, but there's not ultimate answer, like, because there's so many parameters to train. Like, so okay. So question. Parameters, theta. So how many parameters theta? It's a vector of numbers, basically. How many parameters are in ChatGPT? A lot, yeah, but is 100 a lot? Yeah, 100 is a lot to do per hand, like to do how many parameters have ChatGPT?
Well, at least on the order of something million.
On the order of 100 billions.
Even more.
So what we are working, yes?
I don't know if it's comparable, but Llama is like 7 billion.
Yeah, so exactly. So Llama, so the model we're working with, like Llama, 70 billion parameters. Billion parameters. It's like 9 zeros. Billion parameters. And ChatGPT is even bigger. Like, I don't know, who knows, like hundreds of billion parameters. Yeah, so you start with some random initialization of these things, and then you try your best to learn this thing in half a year for a budget of like 20 million euros. And you have one shot, because then you're out of money or you're fired from the company because it's screwed up. So it's really, it's a tricky part. Like if your problem is very small, sure, you can try for many steps and many different initialization, but sometimes you have just one shot. Does it answer your question? Yeah. Okay, cool. I think we should move on. Good. So chain rule, finding a function of, okay. So far we are talking about, so now we are talking about just one variable function, but as we see, like, we have more variables, maybe 3, 4, or 70 billion or 550 billion parameters. So this is number of dimensions we are trying to optimize in. I'll give you an example of a function in like 2 parameters. So we have 2 parameters, x and y. And this is giving us this surface kind of thing, So this is basically, this could be sort of a loss. Loss function is these z-axis, and x, y are those 2. So these are the parameters, and we want to find these parameters, which gives us the minimum of this function. This is sort of it's called a banana function, or Rosenberg function, because the volley is sort of like in banana shape. I think I have some better picture later on. And you want to find a point where this is minimal. This is a very simple example in two dimensions, but we have 3D world, but in reality we have like 500 billion plus 1 dimensional world. You cannot imagine like how this looks like, and nobody can imagine like how this looks like, the shape of the loss. This is very easy, two dimensions plus the loss. In more dimensions, humans cannot actually think about that. Okay, and this is already tricky. So now we have this very fancy function. It's called the Rosenberg function or a banana function with some constants, and we want to minimize it. Yeah, I mean, it's pretty easy. So can we minimize this function? Sure. Now what we're gonna do is these partial derivatives. So we had before the derivatives with respect to the input, but now we have derivatives with respect to each of these input separately. And how we do this, how we compute the partial derivative of function with respect to some input, it's these very fancy symbols. So this is the partial derivative symbol. This is one. So what's the partial derivative of f with respect to x2? This is what this symbol is telling us. So again, it's not a fraction. It's this thing, this Lagrange notation. Oh, sorry, Leibniz notation. So if we have this function, for example, this is another example. So if we have function x1 squared times x2 plus cosinus x3, if we want to compute the partial derivative with respect to x1, you just take the others as constants and do the standard kind of calculus thing. So if you forget this, just take a refresher, how to compute partial derivatives. It might be helpful. And I think we might have something in the exercise actually. Well, sorry for you, like your love to mathematics. Okay, so this is how we do the derivative computing function, sort of, which means for each of these points now, x1, x2, x3, we can compute its partial derivative with respect to each of these variables. Okay, so any questions to partial derivatives? It's basic. So what is this partial derivative saying? We'll come to that later, actually. So it will be the same meaning as the derivative in one dimension, but there is some nice properties of the partial derivatives, and it even has a name. But we talk about the chain rule. So how is the chain rule working with multivariate functions of multiple variables? So let's say we have a function. Oh, this is getting very nasty with the notation. So yeah, this is how it is. We have a function of u and v, and another function again of u and v, and these are differentiable of u and v. Okay, so we have two functions and they have two input variables, the same ones. And then we have a function which kind of takes these two together and is again differentiable with respect to these things. So then we have the compose function. So this is the compose function. It's still differentiable function of u and v. And how we compute the chain rule is, now it looks like fractions. No, it's not. So I'm taking, with respect to each of these inputs, I'm taking the intermediate functions and do this chain rule for each of those intermediate functions. So partial derivative z with respect to the first function, which is the x, and partial derivative of x with respect to the first variable, plus the other path. If you think about it, like we have u and we have v, and they go to x and y, so they go like that. So this is something like computational graph, and they go to f. So these are the dependencies. Does it make sense? Like dependency, so the information flow. Like from u goes to x and to y, and v goes to x and y. These are these two functions, and then these two functions go to f, as we have here. Okay? And then you basically need to consider all paths. So how much is f changing if I change u? This is this thing, or I mean, this notation is horrible. So z, let's call it z. How much is z changing if I change u? So you need to go through this chain rule down here, and through this chain rule down here, and sum them up. So you need to take all the paths, basically, how this if we change, because derivative is telling you, like, if I change x, how much is the output changing? So here, if I'm changing u, how much is the output changing? And I can do this with the chain rule by going through all these intermediate sort of nodes. And this is the multivariate chain rule where it's coming from. Okay? Any questions? Yes.
One question about why we are using like here the partial derivative. Is it because like the parameter is not one like the
Exactly, because you have multiple parameters. You have like multivariate functions. So the input is not just a single real number, but many real numbers. And you need to compute the derivative with respect to each of these input numbers.
So in the case of ChatGPT, the parameters like billions of
Yes.
parameters. we have like partial derivatives for.
Yes. If you have ChatGPT, you have 50 billion parameters. You need to compute partial derivative of the output with respect to each of the parameters. It has a name. So far so good. Like chain rule. Okay. Partial derivatives. It's called a gradient. So it's called the gradient, and the gradient is basically a vector of partial derivatives of the function, which is your loss, with respect to each of the parameters or something which the variables which you can change. So, and we have it, so it's called total derivative matrix, but whatever, I mean, we use it, we call it the gradient, basically. The gradient is a bunch of numbers. It's the partial derivative with respect to each dimension, and the number of dimensions you have, the size of the gradient will be. So this is it. So each of these, and for this cosinus function, you can basically plug them together and get this gradient vector. So if you have 50 million parameters, you have 50 million size gradient. 50 million, yeah, or this is big, of course. And it's called, yeah, it's like that's what's called a large language model. You know, large number of parameters. What are the properties of the gradient? Okay, so think about it. We had this function, like the 2D function, and saying like you're at a point. So the gradient is telling you the direction. What the gradient was. What the derivative was telling you in a 1D function. So just the I don't know x squared or something. What the gradient was saying. Fuck, not gradient. Derivative. What the derivative was saying you again. What was that? Yes.
It points to the direction of the steepest ascent.
The direction of the steepest ascent, which means like where it grows. It tells you left or right, or is it positive or negative. If I go positive, the function will be bigger or smaller. This is for one dimension. Do you know what the gradient is telling you?
Same thing.
It's telling you the same thing. Okay. What does it mean? Like a same thing, but
Like
if you have like you have this banana function, and you compute the gradient. So the first question is, how many items will be in the gradient here from this banana function? 2. Why? Because it has 2 inputs, 2 parameters, so to say, x and y. Okay, so there will be 2 of them. And so what is it going to tell you?
So it's the direction of the gradient will tell us the direction of the greatest ascent at this point.
At a point. So it's gonna tell you the direction of the greatest ascent. Okay, so what is the direction, by the way? How do you say direction? I mean, for one single real function, we had just a positive or negative, but now you're saying direction. So how do you express direction? Oh, it could be actually a vector. Oh, you're right. So the derivative has a very nice property. It's telling you the direction, the vector of the steepest ascent at the given point. What does it mean? If I'm here, for example, the derivative will go. This is very sorry. It doesn't make any sense to show it here. But okay, let me try something here. So this is the banana function. So if I am, for example, here at this point, so here this is rising, right? And this is a part of the. So this is the banana, the valley, and this is the mountain. This is telling me a vector of the rise, something like that, maybe, with just 2 components, x and y, and they correspond to the elements of the partial derivative. Because it's a vector and it has components, so the partial derivative in each of those is telling me, where was I? It's telling me the strength of growth in x direction, and this is the strength of growth in the y direction. And it together gives me a vector. Okay, so it means if I take the negative of the gradient, what does it tell me? The opposite, which means?
The direction of the
Yeah, where to go to the valley. Like I need to go down, and I need to take the direction of the steepest descent. Like I need to go down, and the best way to go down from the mountain, like where does it go like the steepest? I mean, not as a human. I mean, it could be dangerous, but whatever. In the machine learning, just go down. Like this is the straightest point to the minimum. You don't go like up or on the verticals, whatever, or the horizontals. You just go down, and this is what grading is telling you. Grading is telling you Like the opposite of the gradient is telling you, if you go this direction, this is the most straightforward way to go down. Does it make sense? Okay. You can convince yourself by example. For example, this banana function. So again, this is the derivative computing function, which is very ugly, so we're not going to do that. But you can run this sort of gradient. Okay, so we didn't call about gradient descent. But the gradient descent is the same as we have for one real valued function. It's you start at a random point somewhere. But now it's not just a single point, but it's just all these points, 500 billion points, or how many you have. You pick one randomly. Choose wisely, but randomly, whatever. Then you compute the gradient. So the gradient at this point is telling you where to go, which direction to go up. And you take the negative, again, by learning rate, which is again the same thing, and just move somewhere else in the landscape of the loss. And you repeat unless you're exhausted. This is the very same as for one dimension, but now we're using the gradient for multidimensional functions. But in reality, you're just minimizing a function. This is the same principle. Does it make sense? Yes.
I have a question.
Yes.
Why we just need to keep up with the testing? Why just we don't have like heuristics for choosing these random values and choose better ones
like how to choose this? Yeah, it depends. So in some cases, some parameters can be actually wise to initialize somehow around 0 with some Gaussian distribution, like the weights of matrices, for example. Some could be completely random. It depends. So it depends really on the case and empirical evidence, like what works best. So you can use some heuristics, but you also have to have it somehow random. You should start randomly somehow. You can choose it non-randomly if you want. Does it answer your question? Okay, cool. Any other questions? So now let's look at this banana function again. So let's say we started here. Let me just delete this. So we started randomly at this point. So here we see it's very, very steep function here. So the derivative is pointing in this direction, and it might be very high. So it's high, very high values derivative. So it's big derivative. So then depending on the learning rate, of course, you take the different direction, which is this direction, and depending on the learning rate, you decide to land somewhere along the path, which will be here. But it depends on the learning rate. If the learning rate is bigger, you might overshoot and end up here. If the learning rate is small, you can undershoot and end up here. Maybe it's better. So it depends. It's really hard to tell which learning rate to use. But you always know that this direction with small learning rate should give you down, most likely. So we decided to end up here. Okay, here the gradient is going to be a little bit smaller because it's not that steep mountain here. So it goes here and here. So you take the opposite direction and end up at this point. And here the derivative is pointing to this direction. You take the opposite and end up here. And here, it's going, and now you end up in the valley, which is like, it's not completely flat. But you get very small derivative values, like gradient values, very small, because the slope is like really almost flat. And almost flat means like very, very small slope, very small derivatives. And if you're using the same learning rate, you're gonna take baby little steps, because the derivative is small, your learning rate is constant, and you're just taking the steps multiplied. So learning rate multiplied by the derivative or the gradient. It's very small steps, and maybe you say like here actually I'm so far this is not changing, and you're gonna call this a minimum. You say like I'm stopping here. I took like 100,000 steps, and the value of the loss is not changing. Do you know where the true minimum of this function is by any chance? Do you have any guess? Any guess?
I think these two lines right in the middle.
Like this line in the middle, or no?
Like, these two, the ones that have the widest distance between them.
Here, you think here is the minimum?
In the middle.
Somewhere here is the middle. It's a good guess, but then we should have stopped here. You couldn't pass this, because you would have come back. But we were passed through, so the minimum is at 1, 1. It's a very nasty function. very hard to minimize because it's like the gradients are super high most of the time, and here it's very small. And because we're iterating and we said like, okay, we're stopping here because we're not learning anything new in terms of like, well, we're not minimizing anymore, but we should have made it to 1, 1, which is the true minimum.
So is there a reason why it's there, like in the way that graph is drawn, or is it just something arbitrary?
Look at this Rosenberg function. It's a very famous function, and it's very hard to optimize in machine learning. That's why I choose it like it's Rosenberg, I guess.
No, I know.
Yeah.
So like from looking at function or that 3D.
So I didn't get your question then, sorry. What was your question?
That thing that was drawn, I think has a name, but I can't quite remember.
Like this?
Not the right one.
This?
Contour map?
Oh yeah, contour map, yes.
So from the contour map, is there like a way to know exactly where the...
So what you're asking is like, okay, if you're a human and look at this valley, you know where the minimum is. Yeah, but what does it mean? What does it mean to look at the valley? It means you need to evaluate, you can read the landscape as a human, and you know for each point, x, y, for each point you see how it is, how high it is, right? I mean, you look at the mountains like, oh, this is it. So you're basically reading the whole surface at once. You just you're as a human like, look at this and like, yeah, sure, I need to go there. So which means the function would need to evaluate all parameters. You need to read the whole landscape, which means evaluate all the parameter values, and then find the minimum of that. Which means how many parameters you need to evaluate? Like all of them. You cannot look at this contour.
Yeah, no, I think the question was
Okay, sorry.
unrelated. I was just asking like in terms of looking at a contour map.
Yeah. Like now for this example, yeah, I mean the contour map is not detailed enough. Sure, that's a point. Yes, of course. Sorry. Yes. But the point of the minimization is like you cannot just understand the whole landscape just by evaluating because it's just you don't have so much memory or whatever. So you need to take this iterative algorithm to guide you from somewhere to somewhere. It's like, you're in a blind, but the only thing you know, like, where's the next step? Because it's opposed to the derivative or the gradient, and then you need to take some step. But you're basically, the rest is just blind. You don't see any function, okay? So now everything is clear. Like, yes, you have a question.
I have a question because I don't know if the perspective is skewed, but why did we went from the first start to the second start? Looks like we went up.
Yes, yeah, we went up because here, do I have a better picture of this again? Let me just find this. So here you might get, we are starting somewhere here. So you might guess it's very, very steep kind of function here. Like it's very, very steep wall. Which means here, the slope of the gradient is very high. It's very high slope. The gradient is very high. The value of the gradient here is very high. And then we just overshoot it basically. Because we said like we start with some learning rate, which is going to be something, 0.01. But if you multiply a small number with a huge number, because this is like very, very huge slope, you're just basically overshooting. This is what happened here. We should have gone somewhere, theoretically we should have gone somewhere here, but our learning rate was so high, our learning rate was okay. We decided on the learning rate, but the gradient was so high that actually it was so big that it overshooted the volley. That's a problem of overshooting. It's the same like here we had, like in this, you might start here, but if the gradient is very high, you might actually overshoot, the volley here as well. So the thing, how to solve this, smaller learning rate, but then you will have troubles in the volley. Smaller learning rate can get you here, but then you finish somewhere here and never made it to the minimum. Or you can have adaptive learning rate. That's another. Like adaptive learning rate is a thing actually, which is used. But this is the meat and potato, like the basic algorithm. Does it answer your question? Okay. Any other questions? Good. Okay. Let me think. If we make it to the end or not. So, okay. So in reality, our functions are actually bigger. We have much more parameters. So for example, if we want to minimize a function e with respect to all these w1, wk, and the function might look like that. It's a function. Isn't it functional? It's a function. It's a sum of something. and some numbers are constants, and some numbers are the parameters. So basically we need to, these are the parameters or weights. Now we are calling them weight because of the W. And we need to find a partial derivative now of E with respect to W1, E with respect to W2, and so on. Okay, so what is the partial derivative of E with respect to W1 or W0? Can you do that? Can you compute the derivative of this function with respect to W0? Yeah, you can, but you don't want to. Because it's a very nasty function. It's very, there's this sum, then there's this multiplication. Okay, multiplication is logarithm, 1 over something plus exponent, and again, some sum here again. It's like very ugly function. It's very heavily nested function. So you can do it per hand if you really try, but I would say good luck. Like, you don't want to do this because it sucks, like per hand. But you can. Like, people were doing this, like calculus, and you find a derivative, and then you can minimize this function. Yeah, but then imagine like, okay, you know what? I'm gonna change something here. I'm gonna say, I'm gonna do this squared because why not? So you need to go like to compute the derivatives again and again, the partial derivatives again and again, like for the new function, and it's kind of sad. So what would be cool is to have an algorithm that can do this somehow not for us, but they can help us to compute the partial derivatives of very complicated functions. That would be very cool. So you can build any computational, any function, and then for any given point, it will evaluate you the derivative. So it'll give you the value of the sort of the gradient. You need to compute the gradient with respect to all these partial derivatives. So you can do it per hand, but that's not scalable. So we need to build something that will help us to do it easily and easily and cheaply. Okay, so this is the motivation. We need to compute this gradient. Now, I'm afraid we won't go through the backpropagation today because it needs like 15 minutes, and I think we shouldn't rush on that. So we'll start with that later. But just to give a wrap up, why is it important and what we need to do for that? And I think in the exercise we'll touch on that a little bit. So why are we interested in the gradient? Why do we need to compute the gradient of complicated functions? And by the way, this function is actually this is a logistic regression. If you did machine learning, this is basically the loss function of a logistic regression with cross-entropy loss. If it doesn't ring a bell, that's great. That's okay, because it's like some function somebody designed, and it's helpful for training classifiers. I'm not 100% sure this is logistic regression. Should be somehow. So why do we need again? So let's roll back. Why do we need a gradient in the first place? Why are we interested in what is a gradient telling us again? What is a gradient at the point telling us? Yes.
But in which direction to optimize?
It's telling you the optimizing is like what you do with the gradient. But the gradient is telling us if you have a function, it's telling you at a point what direction is it growing as at most. What is the steepest like ascent of the function? This is what grading is telling you. So we are going to use it for minimizing a loss function because we want to have the loss as minimum as possible. Because why do we need a loss as minimum as possible? Yeah.
Because we need high accuracy of
Yeah. We want to fit the training data. We wanna make the error between our predictions, the function, and some training data as small as possible. This is how we express the loss. Okay. We have the gradient. Grading is telling us, for any function, you're at a point, and it's pointing you like the direction of the highest grow. So what are you gonna do this? We're going to say, okay, we're gonna build an iterative algorithm. We compute a gradient for some random point, and take the opposite direction and go a little bit somewhere else, based on the value of the gradient and the learning rate. And if we repeat enough over and over, we should get like very small loss. If we get very small loss, we might learn the function, the parameters, which we are interested in. And this is actually, we actually learn the classifier, because then the classifier learns something from the training data, and it can actually predict all the cats or non-cats in the training data with very, very high, very small loss, which can correspond to very high accuracy, but the loss is more like fine-grained. The accuracy is like 0 or 1, or error, like accuracy is 1 minus error. And this is what we want. We want to build a classifier. And we're using this, this gradient to do the heavy math underneath. So this is it. This is not really rocket science, but kind of a lot of engineering in there. And then the engineering comes in one part. So I want to touch on this before we finish for today. How are we going to express this function? How can we think about this beast? Can we split it somehow? I see you, man. Somebody else. Can we split it somehow? So let me start with something else. This is not a beast. This is tiny little puppy, but can you split it somehow? We did it already in the chain rule. Can you split it? How would you split this function into something smaller? Can you split this into smaller functions? It's a composed function, so we can, of course. How can we do this? Yeah, I mean, we take x squared, and the output of x squared is going to go to the x function, and this is our output. And this means like a flow of information. So this is going here as an argument. Okay, does it make sense? It's very simple. Okay, so I'm gonna add something more. I'm gonna add like, and everything is going to be of logarithm. Okay, so how do you expand this? Yeah, I mean, output of this will go to logarithm of that. Okay, so this is, I mean, we can do the same for this very nasty function, just to look at, functions that we understand in detail and stitch them together. So we can start here. Oh, the sum is kind of ugly. So there is some summation of some vectors. So we get a sum, so there will be some sum. Then it will go through plus, where we add the W0. Then it goes to exp, right? This is this exp. Then I'm gonna do the plus again, where I get 1, which is this, and so on. I mean, we're building things together from very tiny blocks. This is like, if you were ever did you have like formal languages? Did you have to program a calculator? If you have to program a calculator, you would build something like that, because if you have an expression, you need to like, if you have like 1 plus 3 times 4 plus 6, you basically build some sort of a tree, like 1 and 3 goes to this plus, and 4 plus 6 goes to this plus node, and they go together to this multiplication node, and this is your result. Right? So this is what we are building here is a thing called, I mean, now it's more complicated, but at the end of the day, it's the same. Like, there's some functions which are like atomic functions, like exponentiation plus summation again, multiplication maybe, and things like that, logarithm, I don't know. So we're building a thing called computational graph. Okay, so computational graph is a nice way to express composed functions from tiny little elements. And it's a DAG, so directed acyclic graph. It doesn't have to be a tree. In this case, this is a tree, like, and could be even binary tree if you want, but some sort of tree. But could be something like, you can have you can have the, for example, I don't know, you can have this as well if you want. It could be like a sort of a graph where you have different paths. So we have a computational graph, and each node of this graph is some differentiable function, and it has some arguments. And the leaves are some variables like a and b, or some constants, and the arrows just telling like function composition. So if we have here an example, so a and b are some, let's say, numbers, for example, and they go to function f2 as parameters, and they go also to function f3. So this could be, for example, summation, and this could be, I don't know, exponentiation. Why not? So does it make sense? This is how we are splitting complicated graph to, complicated function into pieces and plug them into graph. And if you need to, computations on that, I think we'll touch it in the exercise. Any questions to the computational graph? Because some people see it for the first time in this course, and were just confused last year. So I want to spend more time on that you understand what a computational graph is before we jump to the backpropagation. Any questions on computational graph so far? That's not the case. So okay, we're finished for today, and I'll see you at 2 in the afternoon in the dungeon down there. Okay. So thank you.